Thanks for watching and welcome to the single most important PDE technique of all time, separation of variables. It's a method that will allow us to solve a huge class of PDEs, including Laplace's equation. But what we'll do today, we'll employ separation of variables to solve the heat equation ut equals duxx with zero boundary conditions. I'll explain that in a second, and initial condition x. So what's the scenario here? We have a metal rod, but not an infinite one. This time, a rod of length pi, so 0 and pi. And what we want to do, we want to figure out the temperature of that metal rod at time t and position x. So uxt gives us the temperature at x, and we assume the initial temperature is just increasing, it's just x in this case, and what this means is on the left point and the right point, in other words, at 0 and pi, we're putting ice cubes in such a way that the temperature at the endpoints is always 0. So we assume the temperature at 0 is always 0. That's what u0t equals 0 means. And the temperature at pi is also always 0. U pi t is 0. And by the way, don't worry that this is discontinuous. The same technique works for continuous, initial data, and also here we have a formal solution that might have a jump. So the technique is still valid. Okay, now get ready for a separation of variables adventure. So part 1, separation of variables. So I kid you not, there'll be 6 or 7 parts, but this is one of the techniques where if you do it a couple of times, you will get better at it, I promise. And so what we'll do now, we will assume that our PDE has a special form. So step 1, and this is where we separate variables. Assume u of xt has a special form. I'll explain why in a second. So in this case, assume u of xt is a function of x times a function of t. So we're literally splitting up the variables x and t into 2 functions. So we assume once again that uxt is a function of x and a function of t. So for some x, which is once again a function of x, and some t, which is a function of t. So for example, u of xt equals sine of x times cosine of t, has this form. But if you take, for instance, ln of 3x plus 2t, it doesn't have this form. Have this form. Because notice, it is not a function of x times a function of t. Now, why do we make this assumption? Well, for 2 reasons. First of all, you will see this Ansatz, or this proposition, will help us turn the PDE into 2 ODEs. So it'll make it much simpler, but also one suggestion I have is it comes from modeling purposes, and I invite you to look at the demo. Because if you look at uxt is sine of x times cosine t, then what this looks like, it looks like scaled versions of sine of x. So for instance, at t equals 0, it might look like this, but then at t equals 1, it looks smaller, and then even smaller, etc., etc. So suppose you're modeling the PDE and you notice, hey, the solution looks like scaled versions of sine. That's when it's a good idea to guess sine of x plus some scaling. Because the cosine of t in this case is what's called a scaling factor. Right? Because if cosine of t is 1/2, then it's 1/2 sine of x in that case. And now that we have this guess, let's plug it into the PDE. So step 2. So plug u of xt is x of x times t of t into ut equals duxx. So ut is duxx. Well, now remember, u is x times t, so x of x times t of t with respect to t is dx of x t of t with respect to xx. And well, notice, so x doesn't depend on t, so it comes out, and moreover, you differentiate this function of one variable with respect to t, so this just becomes t prime. And so in the end, we get x of x times t prime of t. And on the other hand, here t doesn't depend on x, so it comes out, and the dos equis derivative becomes x double prime. X double prime of x times t of t. And now, what we want to do, we want to put all the x's in one side and all the t's on the other side. Just like separation of variables in ODEs. And so, for instance, what we get is x double prime over x equals t prime over t. And the question is, where do we put this d? So, as you will see in a second, it's important to keep this as simple as possible. So, any constants, like d or c squared, put them with t. So, put the t here, the d here, because that's okay to be complicated. And now let's analyze this a little bit. And you will see there's a nice miracle that comes out of this. So this next step I like to call constant, as you'll see in a second. And so once again, let's look at what we've got so far. So look at x double prime over x, which, remember, that's just t prime over dt. And consider now the left-hand side. Because it turns out this can be simplified even further. Because notice, this does not depend on t, and so the t derivative is 0. So on the one hand, if you take this quantity, this mystery quantity, and you differentiate this with respect to t, well, since x doesn't depend on t, this thing equals 0. On the other hand, this quantity, since it is t prime over dt, it also doesn't depend on x. So on the other hand, if you take, now we'll change colors, we'll see why. If you take this quantity over x of x, and you differentiate this with respect to x, well, that's the same thing as t prime over dt with respect to x. But again, t does not depend on x, and so we also get that the x derivative of this is 0. So what do we have? We have a mystery quantity. We know it doesn't depend on t, because the t derivative is 0. And it also doesn't depend on x, because the x derivative is 0. So this mystery quantity doesn't depend on x and doesn't depend on t. So what is it? It's a constant. So once again, and so x double prime over x, it is a constant. And we call this lambda. And in particular, what we get now is a very nice ODE for x, because now what we get is x double prime equals lambda x. And similarly, well, t prime over dt is the same constant, lambda, and so we also get ODE for t. Also, t prime over dt, which remember is x double prime over x, and that is lambda, and so we also get another ODE. Namely, t prime of t is d lambda t of t. Now, the question is, which ODE do you solve first? X double prime equals lambda x, or t prime is d lambda t of t? Now, I know it's very tempting to solve this one first, but I highly recommend to resist your urges, because it will just lead you to a mess, and therefore, ideally, always solve the t equation last. Solve this last. Because turns out the x equation will be a bit easier to solve, because next up, we want to deal with the boundary conditions. So now, part 2. So let's focus on the x equation. So far what we have was x double prime equals lambda x. And notice we haven't used any of our boundary conditions or initial conditions. So let's do that now. In particular, let's use the boundary conditions, because they're a bit easier, because they're 0. So now let's use u of 0t is 0. But remember, u is x times t. So this gives you x of 0 times t of t, which is 0. And now, in order to get a nice condition for x, we want to cancel out t. But once again, be careful. You don't want to divide by 0. But notice, t of t is non-zero, because otherwise, remember, u is x times t, which would be x times 0, and that would be 0. And 0 solutions in this case they're not very interesting. I mean, what would it help you to tell? Like, how useful would it be for you if I tell you that the rod always has 0 temperature? And moreover, it doesn't even satisfy the initial condition. So we can legitimately cross out t, and we get x of 0 is 0. Just a little technical detail. Technically, what you do here is you find a point where t is non-zero and cancel out t at that point. So it could be 0 at some points, but not 0 at other points. Very good. So now we have x of 0 is 0, and similarly for the other thing, so u of pi t is 0. That tells you x of pi times t of t is 0. We can cancel out the t's, and we get x of pi. Pi is 0. And so, what differential equation does x satisfy? Well, precisely x double prime is lambda x with 0 condition at 0 and 0 condition at pi, which, if you watch the previous video, is precisely the ODE we're talking about with boundary value problems. It's the same ODE. So what you would do in that case would be do the 3 cases and find interesting values of lambda for which this has non-zero solutions. So part 3 would be the 3 cases. So here is where I would insert the previous video in the playlist, of course. Or you can check out my lecture notes. And what was the result? We found that lambda is precisely minus the square of the positive integers. So the eigenvalues where lambda is minus m squared, where m goes from 1, 2, 3, so minus 1, minus 4, minus 9, etc. And the eigenfunctions. So x of x is just sine of mx. So sine of x, sine of 2x, etc. Which is good. We already found our x functions. And now the only thing really much left is finding the t functions. So part 4. So t equation. So in this case, remember the t equation was t prime equals lambda dt. But now the nice thing is we found lambda, so in other words, t prime is minus m squared dt. And notice this is precisely of the form y prime equals ay, right? In ODEs whose solution is ce to the at. So we can do that to solve for t. And so now what we have is t prime is minus m squared dt. And so in this case, t in theory would be c e to the minus m squared dt. Now here's the thing, we will ignore the constant for now, and the reason is we will reintroduce it later because we'll take linear combinations, or you can think of it once again as taking a basis of solutions. Kind of e of minus m squared dt is the building block of our solutions. So it looks illegal, but will be corrected in a second. But this is all good news. We found t, we found x, so now we find our solution. So conclusion. So for every m, let's say 1, 2, 3, the following is a solution of our PDE. Of our PDE. Namely, u of xt is, once again, x of x times t of t, and that becomes sine of mx times e of minus m squared dt. So we already found very interesting solutions of our PDE. So it's kind of oscillating, but also goes to zero as t gets very large. So it kind of looks like this, at least for large t. Now, the next thing we want to do is take linear combinations, and really in terms of analogies, you can think of it as follows. It's the same thing in ODEs, where you start with building blocks e to the 2t and e to the 3t and take linear combinations to find our solution a e to the 2t plus b e to the 3t. So once again, taking those as building blocks, we will now take linear combinations to find our general solution. So part 5. Linear combos. So I want to remind you, for every m, the following is a solution. So e of minus m squared dt sine of mx. And now, taking linear combos, we get the following. We get that the following is a solution. So u of xt is some constant a1 times e of minus 1 squared dt sine of 1x. So that is the term for m equals 1 plus a2 e of minus 2 squared dt sine of 2x. And that's the term for m equals 2, etc., for m equals 3, m equals 4. But the nice thing is you can conveniently write this as one sum, namely u of xt is now the sum. So this weird sigma symbol means sum from 1 to infinity of am e of minus m squared dt sine of mx. So once again, you take those oscillating functions as building blocks and just take linear combinations to really concoct a solution, to construct your solution that way. So in other words, think of those as little bricks, and now you're building a whole building of the solution. And now the very last thing we have to do, the one condition which we haven't used yet, which is the initial condition. So part 6, initial condition. So what we found so far is u of xt is the sum from m from 1 to infinity of am e of minus m squared dt, and then sine of mx. And now let's plug in t equals 0. So ux0, that is the sum from m from 1 to infinity of am e of minus m squared d0 sine of mx. This term, exponential term, becomes 1, and so in the end this simplifies to the sum from 1 to infinity of am sine of mx. And remember, u of x0 is x. So really now the question boils down to, can we find am such that the sum from 1 to infinity of am sine of mx is x? Which unfortunately we are now stuck, because so far we don't know how to find this. So let me rephrase this. So what we end up with is a big problem, which is also called the famous Fourier problem. So can you find am such that the sum of those sine waves, sum from 1 to infinity of am sine of mx, is the function x? In other words, given the function x on the interval 0, pi, which maybe looks like that, is it possible to approximate the function x with little sine waves? So that sum of am sine of mx is just a linear combination of those sine waves, and the question is, can we find the coefficients accordingly such that that sum gets closer and closer as we want to the function x? So far a very hard problem to solve, but we'll actually be able to solve it using a little bit of linear algebra, which is the point of the next video. Alright, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.